In this lecture, we're gonna do some more examples of trigonometric substitutions, and we're specifically going to do ones that involve the secant function, because the secant function gets a little complicated because of the way the simplifications work. Right. So we talked about this in detail in the theoretical lecture, uh, but I think that may be difficult to follow. I think it's going to be a little clearer when we do it here, when we actually have some numbers to look at. So let's start with this one. I want to integrate this thing here. And the first thing I want you to notice, that integrand is only defined for values of x that are less than or equal to 3 halves or greater than or equal to 3 halves. If we pick numbers in between, then that 4x squared minus 9 is negative and we can't take the square root, right? So you can kind of see, hopefully, where this restriction is coming from, right? What we want to do is we want to look at kind of the right-hand side uh, of the range where this is defined. So what substitution am I getting? Well, you know we're going to use the secant one here. But I am going to simplify this just a little bit first, right? I'm going to start by factoring a 4 out of that denominator. I'm going to go over here to the left to do this. This is the integral of 1 over the square root of 4 times x squared minus 9/4 dx. It's a little easier to see what the substitution is going to be if we can get a 1 in front of that x squared term. Okay, so now let's pull that. The square root of 4 is 2, right? So let's pull that 1/2 out, and then we have the integral. And now let's set up our substitution. Right, my substitution is going to be x equals 3 halves secant theta. Okay, what I want you to notice here, right, is because of this restriction that I've put on x, it's enough for me to require that theta is going to be between 0 and pi over 2. Right? When theta is in that range, the secant of 0 is 1, so that's 3 halves. And as theta goes up to pi over 2, theta goes up to infinity. Remember, the secant is actually undefined at pi over 2. So that is going to generate all of the values of x between 3 halves and infinity, which is the only ones the question says we have to look at. All right, so because we're limiting ourselves to that range, right? Remember, because this is going to be important in the substitution I make over here in a minute. The tangent of theta is always going to be greater than or equal to 0. It's always going to be positive. Right, it's going to be important in just a minute over here with this simplification that we're going to need to do. All right, so what do I have then? This is 1 over the square root of 3 halves secant squared. So that's 9/4 secant squared minus 9/4. And what's dx? Well, dx is 3 halves secant theta tangent theta. Right, so this, let me go ahead and put that in the numerator just to save some space here. So this is secant theta tangent theta d theta. All right, so what's going on in the denominator? Well, first, let's pull that square root of 9/4 off. So this is 1/2 integral secant theta tangent theta over square root of 9/4. That's 3 halves square root of secant squared theta minus 1 d theta. Okay, secant squared theta minus 1 is tangent squared theta. So the square root of tangent squared theta is the absolute value of tangent theta. So let me write that in there. I'm going to bring the 2/3 out. This is 2/3, excuse me, bring the 1 over 3 halves out. So that's 2/3 times 1/2 integral secant theta tangent theta over the absolute value of tangent theta d theta. And this is the point where all of this business about restrictions and so forth becomes important. Because the tangent of theta is always greater than 0, it's always positive, for the values of x that I've been told we're only interested in, the absolute value of the tangent theta is the same as the tangent of theta. So this is 1/3 integral secant theta. Oops, no, sorry, I should put that up on top. Still have to have the fraction. Secant theta, tangent theta, over tangent theta, d theta. Now do you see why that was so important to me? Right? Being able to get rid of that absolute value, I can cancel those tangent thetas, and this is just 1/3 the integral of secant theta d theta. And we've already seen what the integral of secant theta is. This is 1/3 the natural logarithm of the absolute value of the secant of theta plus the tangent of theta plus a constant. And now we need to go back to x's, right? So jump back up here, right? The secant of theta is 2/3 x. Okay, well, good. So let's put that in there for the first part. This is 1/3 the natural logarithm, the absolute value of 2/3 x, plus now I have to do the tangent part, right? Okay, so the secant of theta is 2/3 of x. Let me draw a triangle, just like we did with the other ones we've done, right? I'm going to put theta here. Okay, the secant is 2x over 3. And the secant is 1 over the cosine. So that means the cosine is 3 over 2x. So that has to be a 3. That has to be a 2x. And this is the square root of 4x squared minus 9. Excellent. Now I know what the tangent is. The tangent is the square root of 4x squared minus 9 over 3 plus a constant. And that's it. We're done. Everything is, all the thetas are gone. We're back in terms of x. That's going to be what this integral evaluates to. And I really want to emphasize the restriction on the x's, right? If you try to do a definite integral with this, you can only evaluate it from and to values greater than 3/2. Okay, so how about this one? Okay, now we have no restrictions. Right, we have no restrictions on this. So what we're going to have to do at the end of the day, we're going to have to do this as a piecewise defined function. Right, so let's see what happens here. Right, the substitution that I'm going to use is going to be x equals 4 secant theta. And that's going to make dx 4 secant theta tangent theta d theta. All right, so again, I'm going to go over here because we need a little room with these. This is the integral of 4 secant theta tangent theta over square root of 4 secant theta squared. So that's 16 secant squared theta minus 16, all d theta. And let's see, let's bring that square root of 16 out. So this is 4 over 4 integral secant theta tangent theta over square root of secant squared theta minus 1 d theta. Okay, now here's where it's going to get just a little tricky. That secant squared theta minus 1, right? That's tangent squared. And the square root of tangent squared is the absolute value of the tangent. So this is that's just 1 out in front, right? So this is integral secant theta, tangent theta, over the absolute value of tangent theta d theta. Now, I'd like to do that same simplification, right? I would. But we've got a little problem here, okay? And again, notice what the limitations on the integrand are. X has to be either less than or equal to 4, or x has to be greater than or equal to 4. So what does that tell me about theta? Well, if theta is between 0 and pi over 2, then that gives me x values greater than 4, greater than or equal to 4. Right? When theta is 0, x is equal to 4, and again, it's undefined at pi over 2. It goes off to infinity. We get all the values that are positive. For this range, the tangent of theta is greater than or equal to 0. It's positive, and I can just replace absolute value of tangent theta with tangent of theta, and we're home free. But that doesn't cover the left-hand side. That doesn't cover the numbers that are less than or equal to 4. To get those, we have to let theta be this other side, where it's between pi over 2 and pi. That gets me all the negative values. The secant is negative for those values of theta. So we start, we actually started at negative infinity and go up to negative 4. This should have been, this should have been a negative 4. Hopefully I said that right. Less than or equal to negative 4. Okay, and the problem is that on this side, the tangent of theta is less than or equal to 0, which means for these values, the absolute value of tangent theta equals negative tangent theta. So what I'm going to have to do is I'm going to have to do two integrals here, right? I'm going to have one for theta between 0 and pi over 2, and I'm going to have another one for theta between pi over 2 and pi. Okay, so if we're doing, let me write this further up. If we're doing values of theta between 0 and pi over 2, then this integral is just the integral of secant theta tangent theta over tangent theta d theta. The tangents cancel. This is the integral of secant theta, and we had that on the last slide. This is the log of the absolute value of the secant of theta plus the tangent of theta plus a constant. Secant theta is x over 4 plus what's the tangent? Well, jump back over here. We've got theta. Secant is x over 4, so the cosine is 4 over x. So this is 4, this is x, this is the square root of x squared minus 16. Okay, so what is the tangent then? The tangent is the square root of x squared minus 16 over 4 plus a constant. Now, because this is only valid for values of theta between 0 and pi over 2, what are the corresponding x values? Well, the corresponding x values are x greater than or equal to 4. Now, what happens on the other side? What happens if we have pi over 2 less than 0, less than or equal to pi? Okay, well, then we have to do this substitution. We're going to replace tangent of theta with negative tangent of theta, and the integral becomes the integral of secant theta tangent theta over negative tangent theta d theta. We get the same cancellations, and this is now just the negative integral of secant theta d theta. So and compare that to what we had on the other side. It's the exact same thing, right? It's the exact same thing except for that minus sign out in front. So at the end, we're going to get minus log absolute value of x over 4 plus the square root of x squared minus 16 over 4 plus c for x less than or equal to, you see I did it again, x less than or equal to negative 4. Right, so if I wanted to write this, and I'm really going to have to crunch this in. If I wanted to really answer this question, I would answer this as a piecewise defined function. I would say that the integral is equal to the ln absolute value of x over 4 plus the square root of x squared minus 16 over 4 plus a constant for x greater than or equal to 4. And it's the negative ln absolute value x over 4 plus the square root of x squared minus same thing over 4 plus a constant for x less than or equal to negative 4. And so that would be my final answer, right? If you really want to take this all the way and follow all the little details, right? When we're doing these secant substitutions, and there is no restriction specified like we had on the previous slide, then ultimately this is what your answer is going to be. It's going to be a piecewise defined function. Okay, so how about this one? This one is a trick. I mean, there is a twist in here, right? And you have to kind of keep an eye out for this. Remember, the limits of integration have to cover a range for which the integrand is defined. And this integrand, this is actually the one we saw in the previous slide. This integrand is only defined for values of x less than or equal to negative 4 or greater than or equal to positive 4. Those numbers aren't in either of those ranges. Okay, so this doesn't exist. You can't do this. You can't integrate a function over interval where it isn't defined. So it's a little bit of a gotcha, right? But it's something that needs to be in the back of your mind, right? Just a quick check in the back of your mind, right? But before you start just throwing substitutions around and searching after something that doesn't actually exist. Okay, so how about this one? This one does exist, right? The domain here, I really shouldn't call it the domain. That integrand is defined for values of x greater than or equal to 2 or less than or equal to negative 2. Excuse me. That is the range that we're integrating over. So we can do this, right? And how are we going to do this? Well, I would start by pulling out a 4, right? Make this the integral from negative 4 to negative 2. You pull 4 out of that denominator. Square root of 4 is 2. So that's 1/2 1 over the square root of x squared minus 4 dx. So my substitution is going to be x equals 2 secant theta. So dx equals 2 secant theta tangent theta. And well, let's do our substitutions. 1/2 the integral negative 4 to negative 2, 1 over square root of 4 secant squared theta minus 4 times 2 secant theta. Let me write that on top. We may need the space. 2 secant theta tangent theta d theta. All right, so what happens? These 2's cancel. That's nice. This is the integral negative 4 to negative 2 of secant theta tangent theta. Now, what happens in the denominator? Right? The square root of 4, I can bring that out. So that's going to be 1/2 over square root of secant squared theta minus 1 d theta. Secant squared theta minus 1, that's tangent theta, right? So this is 1/2 integral -4 to -2 secant theta tangent theta over absolute value tangent theta d theta. So what am I going to do with that tangent theta? Right. Well, we're over on the left-hand side here. Right. We need to the values of theta that we're going to need theta to be are ones that give us negative x values, which means we're going to need values of theta between negative pi over 2, between positive pi over 2 and pi. Right. Well, that's the area where the tangent is negative, which means the absolute value of the tangent is equal to negative tangent theta. So that's the substitution that I'm going to make here. This will be the integral from -4 to -2 of secant theta tangent theta over negative tangent theta d theta. Okay, now the tangents cancel. Let's bring that negative out. Negative integral -4 to -2 secant theta d theta. And just like we had on the previous slides, we know what this integral is. This is negative log absolute value secant theta plus tangent theta. No constant this time because it's a definite integral from -4 to -2. Now remember, I know I don't usually change those, but remember those are x values, right? Those are x values, not values of theta. Now, you know, if you watch the first semester calculus lectures, normally I like to switch this back to x and then use the -4 and the -2. Right. This is a case where I think it might actually be better to rewrite that -2 and -4 in terms of theta. And it's going to look a little weird, but just bear with me. Okay. So when x is -2, right, going back to our substitution here, when x is -2, -2 equals 2 secant theta. Secant theta equals -1, which means theta equals, when is the secant -1? That's going to be at pi. Okay, so I'm going to replace this -2 down here with pi. All right, now do it again with a -4. Right, -4 equals 2 secant theta, which means secant theta equals -2. And to be honest with you, I don't really know the secants. I'm thinking, okay, that means the cosine of theta is -1/2, right? And where is the cosine of theta -1/2? That's going to be 2 pi over 3. So theta is 2 pi over 3. And I want you to notice, right, those values are both within our restricted range here. Right, so we're going to replace the -4 with 2 pi over 3. Okay, now we can do the evaluation part. This is negative log absolute value secant pi plus tangent pi minus the log of the secant of 2 pi over 3 plus the tangent of 2 pi over 3. And what do we get here? The secant of pi is -1. Tangent of pi is 0. So this is the log of the absolute value of -1 minus the log of the secant of 2 pi over 3. That is -2 plus the tangent of 2 pi over 3, which is negative, actually. So this will be minus square root of 3 over 3. Okay, absolute value of -1 is 1, and the log of 1 is 0, so this whole term goes away. Right? Then this negative and this negative cancel, and we're left with what's the log of, now look, factor a -1 out of here. -1, 2 plus the square root of 3 over 3. And this is, and I'm just ran out of room, this is the log of 2 plus the square root of 3 over 3. Right? And there's our answer. Right? There's our final value for what this integral equals. Okay, so what's next? That's enough of the trig stuff. That's enough trig for now. In the next series of lectures, we're going to look at methods for integrating rational functions, right? Functions that are one polynomial divided by another. And that's going to rely on a method that you hopefully learned about back in your pre-calc class and have probably forgotten about by now, called partial fractions decomposition. Right, and if you're a little fuzzy on what that was, or maybe you never even learned about it, that's okay. We'll have 1 or 2 lectures about how to do that method before we actually jump into the calculus part.